Happy Monday. Say a few more things. I want to just make sure I can hear you okay, Stephen. Let's start your video.
Start my video. Oh. Whoops, I didn't need to do that. I was wondering why I wasn't on there.
All right, can we get any more light on your face?
So, is that helpful?
Better than nothing. If you tilt your whole body toward the window by like even a quarter of a turn, but I don't know if you could, if that.
My back to the window, like this?
No, the other way.
Yeah, I can do that.
Yeah, oh, that helps a lot.
Okay.
And actually the yellow light helps too. I think it's good.
Okay.
Let's make sure there's nothing weird on your whiteboard. Or confidential.
No.
Okay.
Let me just tidy it up a little bit.
Oh, and it's nice to see a busy chair.
Okay. I don't see my video on here. Am I supposed to?
Yeah, no, you know, I find it really distracting to look at myself, so I always hide my own view.
Well, there I am. Okay.
So we have 3 participants and we have 3 attendees. Ellie, hi Ellie. Ellie's one of our future Huskies. And we have Bill and James. I got your card, Ellie, thank you.
Am I able to see the attendees?
You should be able to if you go down to participants, Steve. So like down on your Zoom, and then but if right now the only thing you can see is your own PowerPoint, then you might not be able to. But if you just bring your cursor down to participants,
I see.
And if you click on that, then you should be able to see that there's 3 panelists and 3 attendees. And so the Q&A, you guys, if you have any questions for me, you can always put Q&A in anytime. And I'll monitor the Q&A. Steve, you don't have to monitor that. But it is helpful once we get to Q&A for you to pull up the Q&A screen, because then you can almost be glancing at the questions as they're coming in, which is fun. Yeah, so we have really awesome sponsors this week, the Patrick and Sandy McClellan.
So I tried to look them up, but couldn't find anything.
Well, yeah, so I can, well, I don't want to, we've already got participants, but they have, I believe, a grandson who is coming to Michigan Tech this fall. And Patrick went to Michigan Tech, and I'm not pulling up the right degree, but I want to say mechanical. Not positive. Oh, so that's nice. We've got chat working right now. I read your message, Ellie. Yeah, so we're going to be learning about material science, and be careful, because this is how you get sucked into becoming a material scientist. You start learning all the cool things about materials. And usually that happens when you take Introduction to Material Science, which is the prereq for it is the first semester chemistry. So I was thinking, Ellie, you should take 1 class this fall. So you're just moving forward in something. So either take chemistry or calculus, just take 1 class. And that way, even at a community college, right? Because you don't have to take all your classes in the same place. Most universities are going to have lots of online offerings.
Ellie is a prospective student?
She's already admitted and is going to be coming next fall. Yep.
Excellent.
And I don't remember her major, though. I don't remember. I think I was told that at one point, or I read it, but didn't stay. All right, so we have 4 people in the as attendees, and so Bill has joined. 2 Bills have joined us. I don't know if the attendees can see each other's names. Somebody tell me if you can. I
I
would love
didn't
to know that.
be able to see that when I've joined in.
I don't know.
Could be me.
If you can still chat, Ellie, tell me if you can see the attendees' names. And if you can't, send me that information in Q&A. We usually shut down chat, Steve, because it just becomes really distracting to monitor it. Yeah, so what did you do this weekend? Anything fun? Did you golf?
No, no. So I mentioned, I used to golf a lot, which is why I've got a bag full of clubs, obviously. But I hurt my shoulder several years ago pretty bad. It was kind of irreparable rotator cuff.
Oh, no.
And so I haven't golfed in a long time, but I'm really looking forward to kind of getting back. I think the time is right, especially pulling these slides out and talking and my clubs again. I'm kind of excited to get back.
All right, I'm turning my volume up. Actually, I'm close to max. You're going to want to make sure you speak up.
Okay. Are you having a hard time hearing me?
You're a little soft-spoken, and of course I'm speaker challenged. I'm using the speaker of I have one big screen. Actually, and I'm too stupid to figure out how to not use that speaker. So I can't make the volume get any higher than a certain amount. But I definitely think make sure you're talking, pretend you're in a classroom.
I just turned it up. Is this better?
That's good.
Okay. Too high, or is it okay?
No, that's actually much better. You can control your own volume?
Yeah, there's an audio settings somewhere.
Cool. I've never wondered if I didn't know that.
Adjacent to the mute button, there's some audio settings that you can manually override the auto setting.
That's awesome. Yeah, no, it's an absolutely gorgeous day here in Houghton. It had been a little hot, but last night it actually cooled off rather nicely, so it was very comfortable. And then today it didn't heat up too badly. I think we're maybe mid 80s. Actually, I'll go check.
So I think I'm guessing it's low 70s or mid 70s.
83 right now under my right outside my house in the shade.
Okay, and not very humid, which makes it nice.
Well, that's what I think made a difference. Because it was getting kind of muggy.
Yeah.
Yeah, no, I didn't. I was working most of the weekend with. It's the July Commission Week where I go and volunteer for ABET and the. So I didn't get outside much over the weekend, but I have been going for a nice walk in the morning. It's really nice. All right, and so we can see your entire desktop now. There we go.
I'm trying to see how I get to that. If I can get to that.
Good.
There I go. Okay.
Yeah, so when did you start learning? Well, when did you first golf? That would be an interesting thing.
Oh yeah, I've been golfing since probably junior high or something like that. I've always enjoyed it, and golfed through high school and college, and actually it was a big part of my graduate program here at Michigan Tech. So we had a lot of golfers in the department, including faculty, and so I organized a weekly golf league for the.
For goodness sake.
Yeah, so that was fun.
With all the grad students.
Grad students and faculty. Yep. So it was great. So
did your PhD advisor golf?
Yep. He sure did.
Ah. Yep. So he approved of this hobby.
Right. And then we had so at that time our president of the university was Dale Stein, and he was a famous golfer. He was a scratch golfer, and so he's actually, so he played with us as well. He would play in the league, and so it was just a lot of fun. So I really enjoyed it. And then after I finished up my degrees, I got a real job with a real paycheck. And for the first time, I went to a real golf store, sporting goods shop, and shop for clubs. And that's where I kind of learned about all these decisions that you have to make between different kinds of materials and different processes and the pros and cons and the urban myth associated with different kinds of clubs and so forth.
Oh, from what,
So that
when
was
we were
probably
talking last week, it made me, so biking, my husband, he's always buying the latest bike. And so it sounds like it's a lot like that. Once there's a better material with better performance,
It's really hard to resist when you see something, you think, wow, this is going to give me an edge, or this is going to make my life easier, or it's going to add to the joy of my life and all this kind of stuff. So it's very good.
And there's sort of having the coolest club in the
right
area, or not, at least not having clubs that are 10 years old or something.
So around 1993, I went to a short course out in California. And this is about the same time when people were starting, or companies were really starting to make new and exotic golf equipment. And attending the short course was another Michigan Tech alum. And this alum, she was the metallurgist for Callaway Golf in San Diego, which was the company that really started it all, this big revolution in new club equipment. And wow, what a job to have, I thought. And
she's a metallurgist.
I love it. She was a metallurgist from Michigan Tech.
Oh my gosh.
How did you get that job? She goes, well, I just answered an ad in the paper. And I said, you golf, right? And she goes, no, she never has. And I go, oh. She could be listening today. She could join us today.
Oh.
We went back to the UP several years ago. So,
What's her first name? I'll see if I
was afraid you'd ask me that when I started talking about it. I can't think of what her name is.
If that person were to be here, I'll try to remember to ask that. Is anybody who ever worked for Callaway Clubs here?
Callaway Golf, yep.
So how did you, did someone in your family golf? Is that kind of why you started in middle school?
Yeah, my older brother was a golfer. He just picked up because his friends, and he was actually very good. He was kind of what I would call a natural, had very good eye-hand coordination. He played on the high school golf team in my hometown, and it was just a fun thing to do.
Mm-hmm.
So.
No one in my family has golfed that I know of. Actually, that's not true. Of course, my Irish grandfather would have golfed. And I remember we had golf clubs. Yep. Grandpa Callahan. That is sort of a Scottish-Irish thing to do. Didn't it start there?
I think it did. Yeah, it seems to be associated with Scotland.
Scots.
Yep.
Yep. So,
I noticed I can speak, but attendees can't speak back, right?
No, but they can ask a question, and that, so we can communicate that way. So if anybody has a question,
they can hear me, right?
We can all hear you. Yep.
So I see Darwin Moon is on the list. So I don't know if Darwin remembers me, but I think you lived in DHH the same time I did. 1976, I think. So he may or may not remember me.
Ask us a question, Darwin.
Yeah.
Or
who's on the list here?
We don't know that chatting isn't allowed because we're kind of, this way we can keep a lid on what's being said about the good old days. Yeah. Just in case there's some story.
Like we can allow him to talk. Should I allow him to talk?
We could if he's, yeah.
It's up to you.
Hey, Darwin.
If this is the same Darwin, then he'll know who I'm talking about here. So Larry Miller was just on campus a couple of weeks ago. So I think Larry was a crony of Darwin, I think, in DHH.
Interesting.
If I got it wrong, Darwin's probably going crazy right now.
Yeah, I know. He's like, it's not me. So what is DHH?
Douglas Houghton Hall.
Oh.
Next door.
And so that's what you guys called it. Was Was it just for men?
No, it was co-ed at the time.
Mm-hmm. No, that's, we still house students in there, don't we?
Yes, yep.
Yeah, I thought so.
It's right next door. It's right out your window.
Well, I'm at home.
Oh, yeah.
I'm quarantining this week because I drove to Chicago last weekend, and we're just being really prudent here. If you had to sleep in a hotel, and you have some interaction with people, even if they're wearing masks. So I'm just self-quarantining for 14 days.
I see Zach Boyden has joined us. Zach is a recent grad of our department from a few years ago. Last I heard, he was in Alaska. So happy to see his name here.
That's good. All right, Zach, we're going to allow you to talk. What's new in Alaska?
Well, hello. I guess about a year ago, I started working as an associate engineer under a professional engineer in metallurgical engineering here at North Iron Engineering. I'll try to keep any like plugging or specific things like that to a very minimum. But I've been up here in Alaska, back in basically my home state ever since I graduated, and now I'm able to be pursuing the exact career that I went to college for. So everything's going pretty great.
Very good. So did you earn your BS here or a more advanced degree?
That is correct. Yes, I got a bachelor's. Actually, well, Dr. Camp was the St. Franklin chair and chair of MSc. I believe you still are, Dr. Camp?
Yep.
Yeah.
Good to hear from you. Send us some more Alaskans. They make good metallurgists.
I think that Alaska is about the furthest away that's still within the states that has the exact same climate, more or less, as Houghton does.
I was up. 37 degrees or so.
Yeah, more or less.
I was just looking that up. I was trying to decide if we were further north than where my mother was born, and I decided we are about 2 degrees further north than, because she was born in Canada, but all the way over in New Brunswick on the sort of lower border against the US on the coast. Yeah, so we're about 2 degrees more north, I think, than that. Yeah, so lots of names I recognize out there. It's good to have everybody here. All right, and we are coming up on the hour pretty soon, so we're going to mute you, Zach, and I think we're good. So we're just back to our regular folks. Yeah, so Steve, you're going to get in trouble if you convert too many people to materials science majors, too many prospective students. The other chairs are gonna, they'll get annoyed.
Well, I'd like to see if that would happen, I guess. So.
Oh, so one of my favorite, so I'm a material scientist, so and I'm a chemical engineer. I started in chemical engineering and then metallurgy and then PhD in material science. And they're all actually pretty closely related. But I did, quote unquote, fall in love with material science when I took the introduction to material science class that was required to be a chemical engineer. And all of a sudden I was like, oh, that was what I liked about chemistry without all the stuff I didn't like. Because it kind of explains the how things work or the why do metals bend and that sort of thing. So Steve's promised, we're going to get started now, but Steve's actually promised to go through the entire webinar without saying the word dislocation. So I don't know if that's possible, but he did say that was his goal. We're going to call it the D word. So if he uses the D word, that's what we're referring to. All right, so let's go ahead and get started. It is on the hour, and it's so awesome to be here for Husky Bites. This is our next to last one in the summer series. As you all probably know, we have these every Monday at 6. We're going to resume the series the second Monday in September and probably go for another run of 10 to 12 Husky Bites webinars. We're going to keep them Mondays at 6. I would like to acknowledge the sponsorship of Pat and Sandy McClellan. Thank you so much. I am honored that you have sponsored us and appreciate the support for students. Every penny raised in sponsorship goes for students this fall. All right, next slide, Steve. If you fall off our radar and you can't get back in, just join us on Facebook Live. Next slide.
That's me.
All right, and so it is my strong pleasure to be able to introduce Dr. Steve Kampe, who is the St. John Professor and Chair. So that's an endowment that helps support the Material Science and Engineering Department. So Steve earned all of his degrees from Michigan Tech, and we're going to kind of hear the story of how he worked his way back around the world and wound up here. But I'm going to let him tell that part of the story. So Steve, take it from here, please.
Okay, so thanks very much. And I'd also like to thank the McClellans for their sponsorship of this Husky Bites. Okay, so as you can see, the title what I'm going to talk about today is, it's called There's MSE in Your Golf Bag. And it's not a bad thing, okay? It's a lot of good things associated with MSE and the different kinds of materials of construction. And so this is kind of a hobby of mine. I like to kind of decoding the material science in kind of everyday objects. So why did the engineers choose this particular material for this application? So I won't go through this. This is a busy slide about kind of my path and the land that I have trod on the last 30 years or so. But I did want to mention I grew up in Lower Michigan, a town near East Lansing. And I came to Michigan Tech in the mid-'70s and ended up staying for 10 years, got all 3 degrees, and then headed out east, Martin Marietta, and then a few years at Virginia Tech, and then in 2008 was able to come back. So kind of a common thread in this complete circle are titanium alloys, and composites and processing methodologies for composites. So it's been kind of a constant thread through my career. Okay, so just real quickly, how do we view material science and engineering? What is it? And I mentioned here, we always talk about just 1 degree of separation between kind of any aspect of what we do. So obviously, we design things based on, for some application or performance, but the performance is only 1 degree of separation from the process that we use to make it, the structure of the material that we use, and then the properties that we measure to kind of justify that. Okay, so I'm going to talk about the clubs in my golf bag. So that's my golf bag, obviously. And then from a performance point of view, we have different kinds of metrics and different kinds of requirements depending on the part of your game that you're working on. And that makes kind of for an interesting case study. You carry a club for a particular reason, for a particular job, and how it's made perhaps caters to that. Okay, so here is the first poll. So Sue, are you going to start this or should I? So I want to ask a question here. How often has a new or exotic material influenced your decision to make a major purchase? Okay, and so the obvious examples might be sporting goods, so golf club, obviously, bike frames, tennis rackets, baseball bats, things like that.
It influences my husband once a year when he needs to buy his next bike. Right. I'm just saying.
Or vehicles, the Audi A8, one of the first, aluminum intensive vehicles, Ford F-150, Teslas, DeLorean, maybe somebody here bought a DeLorean, okay, that kind. So, all right, so I'm seeing.
The answers are pouring in. It looks like 63% of people say occasionally, i.e. more than once.
But no one says never, okay?
No one says
thank
never.
Goodness for you people. That's all I can say. This is great. Okay.
Well, lots of us are engineers and we can afford, the best materials.
Right.
Sometimes, okay. Occasionally.
So this is, this kind of states my case. So materials are, they're kind of an interesting aspect. They motivate people to kind of spend money people, especially with sporting goods, it's a lot like the Department of Defense. If there's a sense that the materials can give you an edge, in what you're trying to do, people will tend to spend money on that. So thank goodness, and thank all of you people for that. Okay, so let me kind of proceed here. Okay, so what I'm going to talk about today is I'm going to talk about 4 ways that you strengthen a metal. Okay, so there's actually more than this, but these are kind of the big 4 that we use kind of on a daily basis as MSEs. So we can alloy it, we can throw in some hard particles. We have some other names for these things. We can beat on it, or we can reinforce it with strong fibers. So I'm going to talk a little bit about these. And the reason these work is, again, because I found each of these in my golf bag. All right, so let's talk about this. Whoops. All right, so alloying. Okay, so the next quiz that we're going to have is I'm going to ask you why a 14 karat ring is more valuable than a 24 karat cousin.
So,
all right, so the way alloying works, okay, so not quite yet, Sue, but all right. So the way alloying works, you heat a metal until it melts. You add what I'll just call a little bit of another element. You allow it to cool. And what you end up with is a material where you have guest atoms. That's the little bit of another element. They find a spot on the host lattice. And the guest atoms don't quite fit right. Okay, they're either a little bit smaller, a little bit bigger than the host. And this causes the host lattice to elastically distort, kind of at the atomic level here. And as a result of that, the host material becomes harder and stronger. And
Why? Wait, why?
Because of the D word, which I promise not to mention.
I'm trying to
They're involved. They're involved with everything. Okay, so I actually had an experience. I mentioned the D word in a meeting I had a long time ago in a previous life, and I really got chewed out. They never wanted to hear that word.
It's too technical. So
Well,
just spoiler, D is dislocation.
Right. So here's a convenient plot I have from a textbook. This is for copper. So here's pure copper, and as you add percent of an alloying element, it gets stronger. The yield strength goes up. And copper zinc as what kind of proper name or common name?
Brass?
That would be brass, and copper nickels, for example, and then bronzes, for example. All are strengthened by this mechanism. So you add a little bit, you don't overdo it, you can get some significant strength increases. Okay, so what's this got to do with golf? So let's go to the golf bag. Here's my golf bag. And then here's an interesting club. There's this kind of orange or brown club. It's my sand wedge. And how did I end up with this? Well, you go to a golf shop, and the salesperson told me, I said, what are these? This is interesting. They look funny. He says, these are beryllium clubs. He said, beryllium is a really hard metal. Using these clubs will allow you to finesse the ball. And by finesse the ball, you've probably seen, like Tiger Woods on TV. He throws a shot onto the green, and the ball backs up or something. So, you put spin on it to make the ball do magical things. Okay, so I'm a metallurgist by training. I knew it wasn't beryllium, okay? It's brown and so forth. Actually, it's a copper alloy with a little bit of beryllium added, okay? So beryllium's kind of a special element in copper. So I've circled the beryllium response on this plot, and you can see you get huge strengthening, so you can make copper about 4 or 5 times stronger than its pure form, just with a small amount of beryllium. Okay, so I didn't buy a whole set of beryllium clubs, but I did buy a sand wedge. I was interested in it. Did it allow me to finesse the ball? Not at all. Okay, but it looks cool. People ask about the club, so it's a good conversation starter.
Well, these would all have about the same elastic modulus, wouldn't they?
So what they tend to do in golf club design is they try to make the club head about the same weight. So the swing dynamics, the dynamics of your swing are similar from club to club. And there's different tools that you can do that. Turns out copper has a density not unlike steel. Okay, so you know you can get pretty close, but that's a good point. So weight-wise, they're going to be pretty similar. Okay, so so that's okay. So here's my quiz. So
relaunch that one.
Relaunch that one if you could, Sue. So I'm wondering if we can we? Okay, yeah.
Yes.
Why is a 14-karat gold ring more valuable than its 20-karat cousin?
Define value.
Cheaper, it's more wear resistance, all of the above, since many of us are engineers. I should have had none of the above on there. All right, that's right. So who wants a 20-karat gold ring? I mean, you know, they wear away and so forth. Okay, so, but that's an example of solid solution strengthening. Okay, so a gold ring.
I would argue it is more valuable because it has more gold in it, but it's less useful.
Right. So a little bit of tongue in cheek here, but okay. All right. So let me move on. Okay. So, all right. All right. So that was alloying it. Okay. Second strengthening mechanism. We're going to throw in some hard particles. I think I maybe skipped the slide. Yeah. Okay. So the recipe here is heat a metal till it melts. I'll just say add more of another element, okay, meaning more than a little bit. Allow it to cool, okay? And so what happens is these excess additions exceed the solubility limit of the host material, and you create precipitates or particles that precipitate kind of within and around the host crystals. Okay, so these particles make it more difficult to deform the host material because of that D word, okay, they're involved. Okay, and so we would say that the host material has been strengthened by something called precipitation hardening. Okay, so what difference does it make? Okay, so let's go to the golf bag. Okay, so metal drivers and irons. Okay, so when I first started playing golf, all drivers were made out of wood. Sometime around the mid-80s, they started making them out of metal, okay? And one of the first companies to do that was Callaway Golf, okay? And they made a product called a Big Bertha, okay? And the reason they call it Big Bertha is because it was a lot bigger than the wooden shafts. Okay, so here's my Big Bertha. On the bottom of the head, there's a little inscription, 17.4 pH. That happens to mean something to me as a metallurgist. Maybe it means something to you. But what that means, I can recognize that as referring to a stainless steel. Okay, so 17.4 pH stainless steel. Metal woods, they still call them woods because that's historically what they are made out of, and irons. Okay, so when I was shopping for these clubs, the salesperson told me these are very strong clubs. They have a huge sweet spot, meaning there's a bit large area on the club that you can still get a good shot off of. Using these clubs will make your game more consistent. Okay, so I'm a metallurgist, so I try to decode things here. Turns out it's true that they are very strong. This was an early aerospace alloy from the early 50s. If Bob Carnahan is with us, I'm sure he's got a backstory associated with this. They are stainless steel, as I mentioned, made even stronger by precipitation hardening. So there's a P and an H there. And the 17.4 tells us something about the composition, which tells us something about the structure of the material. So the 17 refers to chrome, okay, so that makes it a stainless. And the 4 refers to the amount of nickel, which is also an influential element in establishing the properties of a stainless steel. Okay, so how did this affect my game? Because they are so strong, they can be oversized. So my Big Bertha is now much bigger than my wood, my Jack Nicklaus Golden Bear wood that I used before that. Okay, because we can use less material and you could hollow it out. Okay, because they are so much bigger, it's harder to miss the ball. Okay, so consistency there. And something that's not said but is also quite important is they're also isotropic, which some of you might recognize that word, but that means the properties are the same in all direction, unlike my wood. Okay, so think about when you were in Little League and the coach sent you to the plate with your wooden bat, he always reminded you to turn the trademark towards you. And that's because you want to hit the ball a certain direction of the grain, otherwise the bat would break. Okay, so that was a problem with early drivers.
I did not know that.
Okay, so my woods or my drivers are titanium, or excuse me, 17.4 pH. Nowadays, most drivers are made out of titanium. Same kind of idea. Titanium's half the density of the stainless steel, so you can make them twice as big, twice the volume. So they're extra oversized and unfortunately extra priced too, because we'll pay for it. Okay, these kind of things.
Kind of like bicycles, right? Yeah.
That's right. Okay, so that was my second strengthening mechanism. Third one, I'm going to call it beat on it. And so the recipe here is find a piece of metal and deform it into a new shape. Okay, so this is a common way to process products into some kind of useful shape. Okay, so the MSCs.
Why does it make them stronger, Steve?
Oh, the D word is involved here again. Okay. The universal explanation, which is why this person, I got chewed out. It's the universal explanation, but you can predict nothing with it. So, okay, so MSCs and other engineers among us know that when you deform something plastically, okay, you impose a shape change onto the material. That plastic deformation makes the metal stronger. Okay, and so if you've ever tried to like plumb copper tubing in your house, you probably noticed that you can only bend it once. It's almost impossible to bend the original shape back again. Okay, that's because you've made the kink area stronger. Okay, so we say that the material, if we do this on purpose, the material is strengthened by way of cold work and is referred to as wrought processed alloy. So you hear wrought alloys a lot in movies and in the popular media and so forth, kind of implying something that's been made strong, okay, or high quality. Okay, so both of those I think are relevant. Okay, so let's go to my golf bag and where does this show up? Well, it turns out when you buy clubs, one of the first decisions you have to make at the sporting goods store is the salesman's going to ask you, do you want investment cast irons or do you want forged irons? And so the one on the right here circled is an example of a forged iron. They call them muscle back, or sometimes they call them blades. And you can tell it's forged because the club head is pretty flat and it's pretty featureless. And that's because in the forging process, when you press a metal between two dies, and then you separate the dies after the process is complete, you need to be able to take it out. It needs to be able to be pulled out relatively easy. If the face or the club was too complicated or complex, it would stick to one side of the die and it would be difficult to get out. You can get around that through investment casting, which allows you to make more intricate shapes. And so the club on the left is an example of investment cast, and we know that because it's got this kind of deep cavity in the back of the head. Okay. All right. So so the salesperson shared this with me, and then this was an area that a lot of golfers had strong opinions on. Okay, so I would hear things like forged club offer more power than investment cast clubs. Cast clubs are perfect for the amateur since they should sacrifice distance for consistency, meaning consistency is the big thing that makes us amateur. Inconsistency is the big thing that makes us amateurs. So why not give up some distance in order to be consistent? Okay, so again, metallurgist, the main 1 degree of separation between performance and in this case, processing. So forging imposes some club head design limitations, as I mentioned. Okay, casting enables the design methodology known as perimeter weighting, okay, which means, again, similar kind of weight between the two clubs, but you can kind of concentrate all the weight at the very perimeter of the swing. And they even sometimes supplement this. They tuck in some tungsten or really high density stuff into the club. that again kind of throws the weight to the outside of the swing. Okay, are they more consistent? And this is actually something that might actually be true. I think it's probably true, and it's probably due to the perimeter weighting and the influence that that has on, you know, the dynamics of your swing. They do talk about larger sweet spots, meaning clubs are more forgiving for slight mishits. Is there more power? I think this is an urban myth. I think, you know, when new products come out that make life easier for the amateur, there's always going to be pushback from people that have worked real hard on their swing, and they don't like it when life is made easier for amateurs or hacks like me.
You don't seem such an amateur, actually, Steve.
Yeah, I am. Okay, so that was strengthening mechanism of 3. Number 4, reinforcing with strong fibers. Okay, so this is kind of a big one. This one's been around in the sporting goods industry for a while. So the recipe here, the processing method, is find some superfine fibers, something like carbon, graphite, boron, glass, things like that, and then embed them in epoxy or some other plastic. Okay, and so most of us as engineers know that filamentary forms of materials can exhibit extremely high strengths. So in material science, we often learn early in our material science courses about the theoretical strength of materials. Okay, so the strength of a material without one of these defects, for example, you can get really high strengths. Okay, it turns out the finer you make these materials, the smaller you make them, you can actually start approaching those theoretical strengths, which are related to the strength between bonds between individual atoms. Okay, so the problem with these high strengths is they tend to be not very tough. Okay, so an obvious solution to someone was, let's take a whole bunch of these very fine forms of materials, a whole bunch of them, and glue them together, maybe with a polymer. So now you've embedded a whole bunch of very high strength filamentary materials into a polymer. Now you have a bulk material. So you get the strength from the fibers, you get the binding capability, you get the glue from the polymers, okay? And you kind of get the best of both worlds, okay? So polymers aren't very strong, and obviously not going to work without the reinforcement. Okay, so at the bottom, so we call these are composites or hybrid materials. We're taking 2 different materials, combining them, and trying to get a 2 + 2 = 5 kind of effect. Strength of defined filaments can be combined with the positive attributes of polymers to form engineering composites. Okay, so golf bag. All right, so composite shafts. Okay, so another huge kind of breakthrough in golf and sporting goods is using composite shafts, you know, for sporting goods or bikes, for example. So I have here circled, you know, two composite shafts, and then here's my old Jack Nicklaus wooden driver with a stainless steel shaft. You still have both options available today, and there might be reasons to do that. Okay, so what did the golf salesman tell me? He referred to these as graphite shafts. They can be customized to fit your swing. They're not for everyone though. Okay, so actually, whenever anyone tells you they have like a graphite bike frame or graphite shafts, it's not really just graphite. It's usually an epoxy or some kind of polymer with embedded layers or fibers inside. Okay, and so what's nifty about composites is that you can engineer the properties by changing the relative proportions of the fiber versus the polymer that you put in there. Okay, so one of the challenges that we have in composite designs is these are inherently anisotropic. So I used that word before. So this means that depending on how the fibers are oriented, the properties could be different in different directions. But if you're clever, you can engineer these to be what we call quasi-isotropic. So you can embed fibers in lots of different directions and make it isotropic-like. And the reason this is kind of helpful and useful is turns out the flexure of the shaft during the swing can be again custom to to your own swing, how hard you swing, how much power you want to impart to the ball, and so forth. But swing timing becomes real important. Okay, so here's an example, customized shaft. You talk to a salesman, he'll ask you, what kind of shaft you want. You want extra stiff, or do you want extra whippy, or something in between? There's benefits of both. Amateurs tend to be over on this side. Sometimes, unless you swing really hard, you might want to be over on this side. If you go whippy, you can get really high club head speeds, because when that Jack Nicklaus is swinging right there, when that straightens out, it's going to whip forward and it's going to impart a lot of velocity to the ball. Okay, in sophomore mechanics class, this is the equation that's in play here. So Jack is holding a cantilever beam called a golf club. There's a force being applied to the end, and there's a deflection associated with that. And then the denominator here is the elastic modulus, which we can customize through compositing. So here's an application of a very fundamental engineering equation to the golf course situation. Okay, so here's I think this might be my last quiz. So I'm wondering, why are composites so expensive? Is it because they are highly engineered, require extra careful processing, making them justifiably expensive? Is it because they often require very labor intensive, very customized processing I mentioned? Or is it because people will often pay irrational amounts of money for an edge? Or will people often pay for the cool factor associated with composites, or all of the above? So
Okay.
This is easy, okay? So,
And so, yeah, all right, wait, so we have a chance to fill out the poll. All right,
wow,
oh
look
my
at this.
God, you didn't sucker anybody in on this one.
Yeah, oh, it's just all right.
Yeah.
I
So
should have also
overwhelmingly,
none of the above.
90% is all of the above, with a couple of people in each of the other categories.
Right.
So all of those things are true. They're highly engineered and expensive. They're labor intensive, customized. People will pay irrational amounts of money for them. People will pay for the cool factor.
Right. One of the interests that I've had through the years with material science is understanding why people will pay, what they see in materials that makes them want to pay. And this kind of my interest started with the original iMac. The iMac had a look that made people happy. And, we were in discussions like, what is it, how would we describe, what material property translates into making people happy, so that this is kind of an ongoing discussion. And the cool factor is, that is a material property that we sometimes work with, okay? And composites usually score very high in that area, okay? All right, so finally, in my golf bag, okay, so we're a material science department, so we're an equal opportunity department when it comes to materials. So we've talked a lot about metals. I've mentioned polymers. There is a place for ceramics in the golf bag. And here's an alumina putter that I have, okay, that I use. And again, ceramics have made an attempt to get into the golf bags in some of these high impact applications like drivers. So Coors and some Japanese companies were making ceramic golf clubs at one point, or drivers, but I was just looking for them on the internet recently and on eBay, and I couldn't find any of them, which probably means that they haven't been sustained. But they're fine for putters, okay? So putting, a lot of times it's feel and emotional closeness to the material and to the club that dictates. And so I wanted to include ceramics in my presentation as well. Okay, so finally, here's my last slide. This kind of sums everything up. So this was an article that I pulled out of USA Today a long time ago, but it kind of sums things up. So this was a series in USA Today called The Good Life, a user's guide to pursuit of happiness. Okay, so as metallurgists and material scientists, we hope that we can be a part of that. And then the title of this particular article, which kind of fits with the theme today, golfers get into the high-tech swing, designs and materials also drive up prices. Okay, so I mentioned in my intro, one common thread was titanium alloys, composites. I had a career with the aerospace industry. Turns out sporting goods and the aerospace industry have a lot in common. Again, if you can present people with the opportunity, give them a material where they feel they can get an edge, real or perceived, they will usually pay for it. Okay, and again, it can result in happiness. Okay, so that's what I have, and it's just fun to do this kind of thing, obviously, for at least for me. Okay, so that's what I have. So I'll turn it back to Janet, and she can moderate the rest of the way.
Right. So thank you so much. Dr. Kemp, it's been an honor to hear your webinar. I do want to again acknowledge the Patrick and Sandy McClellan. If anyone's interested in sponsoring a Husky Bites webinar, just send Bryant an email, and his email is weathers@mtu.edu. And this is in support of students. And we have students in need here this fall at Michigan Tech because family, employment has changed for some of them. Our next session, this will be our last for the summer, is August 3rd, 6 p.m. This features mechanical engineering professor, Dr. Gordon Parker, who is going to be speaking. He's going to be tackling a pretty tough subject to explain in 20 minutes, which is control systems. And I'm really looking forward to that. I invite you to join us. I do want to point out that we are going to be resuming Husky Bites at popular demand from the feedback that I've been receiving from many of you. Thank you so much for your emails. We're going to start the second Monday in September, and I will put that date up next week, actually. And so I did want to point out a couple of things. So we will be sending some mailings out to folks. If anyone in particular would like a mask, send me an email with your address, and I'd be happy to get one in the mail for you. Hopefully this week. I'm 1 week behind from last week, but I hope to get a whole bunch in the mail this week. We got another batch of delivered and sewn by hand. We're buying them from one of the local seamstresses. And please load in your questions. I noticed we have 4 open questions, and we're going to start working on those next. And those can be typed in at any point. So we have a tradition of kind of staying in until the last question's answered. And Dr. Kemp has kindly agreed to stay and answer questions. And I just want to thank you again, Steve. I learned a lot, and I'm fascinated by materials. It's just a fascinating field. Okay. So we have a few questions already out there. So that one of the earliest comments actually happened before the hour from Paul, who says, my golfing experience consisted of joining the company golf league on a 9-hole course with a set of garage sale clubs. The company computer was set up to track our scores and assumed that all scores would just be 2 digits. The first week out, I blew out the program with a 3-digit score.
Yeah.
Nice job, Paul.
Yes.
And Glenn, when you started showing the first pictures, and I noticed this too, I'm like, whoa, he's used those things. He said they look well used because we could see dings and divots in them and things.
Well, the first club I showed was the Beryllium club, the copper Beryllium. And, one of the, half the people that see those say, wow, that's really cool because it's got this patina on it. And it looks a lot different than when I bought it, but you get this kind of oxide patina on it. Half the people think it's ugly. Half the people think it's, wow, it's really cool. But you're right, it does look well used.
All right, and so this next question is from Leonard, who asks, what was your primary reason for buying the Alumina putter? Was it the cool factor?
Oh, that's a great question. So I had given a version of this talk to some colleagues before, several years ago. And there happened to be an engineer in the audience. It was to prospective students. And the father of the prospective student actually worked for Coors Ceramics in Colorado. And after I, a couple weeks after I gave the presentation, I received that putter in the mail as a gift from Coors Advanced Ceramics. And his point was, next time you give this talk, you need to include
Plug Coors.
ceramics.
There we go. Fair
So
enough.
that's a good, yeah, so, yep.
All right, this next question is from Walter, who earned, like you, earned a BS, MS, and PhD all at Tech and the years between the years 69, 78. Steve, Walter states, many of the presenters before you talked a lot about the impact of surfaces on what they were researching. Can you elaborate on the role materials play in surface and surface energetics in all of these disciplines? P.S. I'm not great a golfer, but I do have a patent on CU because of its twining capability.
Twinning, probably.
Twinning. Yes, twinning.
Maybe maybe he has a patent for materials that dampen. I'm just guess, or maybe it's high toughness or ductility or something like that. So that's a tough question. Can you elaborate on the role materials play in surface and surface energetics in all these disciplines? I'm just gonna have to say probably no, I can't.
I know, I was gonna say, we should put your email up here. What's your email, Steve?
Oh, Kampe, K-M-P-E, @mtu.edu.
I think you guys should have a conversation.
Yeah.
And I'm not sure what CU is. Patent on, what would that stand for?
I'm thinking it might be copper, but
Yeah.
Not
Oh,
sure.
just copper.
I'm not sure.
Yeah, of course, copper twins like
Our
crazy.
twins in copper, right?
Yep. All right, the next question, also from Walter. Here, I will show you the mask. Can you guys see this? So it has a Husky. Yes, it does have a Husky on him. So this is I call this the medium/large, because they're all too big for me. And then this one is the large size one. So if you do ask for a mask, tell me if you need because this is kind of more like an extra large. So do you need the slightly smaller one or the kind of bigger one? And they do shrink in the wash. Paul asks, given temperature variation considerations, should one take into account playing in the Keweenaw versus the rest of the world?
Okay, good question.
Have you played in the snow, in other words?
Actually, yes, I have. And, I have my own experience. I don't know what the kind of the accepted current response is, but certainly whenever I played in the cold, it was more of a golf ball thing. You went to a lower compression golf ball, and so you wouldn't kind of shatter your hands or, and so forth. I'm not aware of anyone that's really talked about their clubs, the material of construction of their clubs making a big difference as a function of temperature. But I'm probably wrong. I'm sure there's probably somebody that feels that's the case, but so I'm not sure about that. I think you're muted, Janet.
No, that's good.
Okay.
All right, next question is from Michael. Why haven't tungsten carbide cobalt inserts been used for woods, quote unquote? Would that exceed the coefficient of restitution allowed by the rules of golf? Ooh, that's a real technical one.
Okay, so I'm not sure, to be honest with you, that they haven't utilized, some inserts inside drivers. So I mentioned, I didn't have a picture here, but the current drivers are about twice or maybe greater than twice the volume. The heads are about twice the volume of, my stainless Big Bertha, because they're made out of titanium, and they're also hollow. And one thing I've never done is gone inside one of those things. So I'm pretty sure there's a fair bit of engineering design work on weight placement that they kind of tuck on the inside and so forth. And so there could be some materials like that. So you mentioned the coefficient of restitution. This is not a material property. It's a measurement that they make with golf clubs. It's related to the velocity of the ball as it leaves the club relative to the velocity of the club at that moment. Okay, so about the time when all these advanced materials started coming around, the United States Golf Association found themselves in a position where they started kind of having to make some rules about, the limit of things and so forth. And this was one of the properties or the measurements that they made that would dictate whether a certain club was legal for probably the pros and so forth. And there are actually a lot of clubs that kind of that violate this coefficient of restitution, meaning the velocity of the ball, again, as it leaves the club head, is too fast, okay? This was exactly the same issue associated with aluminum scandium bats. Remember a few years ago, and why the pros don't use aluminum bats is because the velocity of the softball, the baseball leaving the bat, that's a coefficient of restitution issue, was too fast. And it was, in that case, it was a safety issue. So I'm not sure if how they weight clubs on the inside, if that's going to affect the coefficient of restitution. It probably will. There was a popular material that was developed about 20 years ago, actually by a professor, a well-known professor in material science in California. He was making what they call liquid metal golf clubs. So liquid metal referring to the fact that it had a non-crystalline structure. So here's the structure, 1 degree of separation. And actually those were cast for many years, I believe it, by Helmet downstate Michigan. But I believe those clubs, and again, a little bit of kind of myth here, mythology, I believe those clubs were eventually ruled to be illegal because of this coefficient of restitution issue. So the material scientists went too far in this case, okay? So created what the USGA would consider a kind of an unfair advantage. And so that was interesting that they've started to do that. So.
No, it's good you knew about this, because I was reading that and I was like, what? Not sure I've ever seen that materials property before.
Yeah, it's not a property, it's just a measurement. So, yeah.
So Steve wants you to flash back to one of your earlier slides, which had a unique MSE logo. He wanted to get a screenshot of the logo, but he wasn't fast enough. It was a slide with a sketch of a golfer on the left. And Steve is a metallurgical engineering alumnus. So we'll let you find that one.
Let's see, I got it. Was it, might have been the title.
He's gonna need to tell us if we found the right slide. By
that one?
Oh, no, it was probably that one. All right, so leave that one up for a little while and we'll see if that answered his question. If not, Steve, ask the question again. Very interesting. So, all right, the next question is from one of our audience members who says, about halfway through the presentation, I believe it was said that perimeter weighted irons smoothed the swing. Did I get that right? And why is that?
Well, I probably did say something like that. So, there is, I don't understand the dynamics or anything, but there is something to the fact that if you kind of weight the outer radius of your swing, that kind of smooths out, has the potential to kind of smooth out your swing a little bit. And so you can think about, something on a rope, for example, a weight on the end of a rope, you swing it, the heavier it is, rope's gonna stay taut and so forth. Might be something like that. I don't know. I'm not aware of an engineering measurement. Probably this is where we would maybe consult our mechanical engineering colleagues, how they would describe that effect. It's an inertial effect somehow.
Mm-hmm.
Yeah.
Good. All right. And then Cameron asks, have you ever looked at any of your golf clubs under our electron microscopes? If not, what is your favorite thing to look at under the microscope for teaching or for fun?
Okay, so actually I never have looked at these clubs under the microscope. And the main reason is I would have to cut them up. I'd have to chop them up into little pieces so they would fit in the chamber, which tends to be relatively small. So I guess another reason might be, I have a pretty good sense for what the materials are. And so I wouldn't really expect them to look any different than what I expect, unless, big unless here, unless they broke or failed or fractured, in which case, chopping it up wouldn't be that big a deal. And we could kind of look to see why that particular club or that component failed or fractured. And sometimes we get clues by looking at it under the microscope. So we find defects or inclusions or things like that. So
Oh, go ahead. Go, sorry.
best favorite things to look under the microscope. I like looking at, obviously I like looking at metals. I like looking at anything that's, we call it multi-phase, meaning there's a variety of different kinds of contrast in what we call the microstructure.
Mm-hmm.
So they can be quite beautiful and artistic. If you look at the blog that Kim Geiger posted today, we have some photos in there with some micrographs that were taken in color at high magnifications. And they really can be, very artistic looking. They can be very beautiful. And I really like, well-polished optical micrographs would be my favorite. Even though we have electron microscopes, those have their role and they're phenomenal in terms of the technology and so forth. To me, there's nothing like a well-polished, nicely prepared optical micrograph. 500x, something like that.
Where you can see all the grains.
Yep.
This question is from future student William. What materials would you say are the materials of the future?
Oh, so, well, let's see. There are some exciting materials that are receiving kind of a lot of funding for their development. There's a material called 2D graphene, which is has a lot of potential. So graphene, so I had talked about graphite in my presentation. Graphite is a form of carbon. Graphene is a similar form of carbon, similar to graphite, but it's a two-dimensional structure. And so you can get spectacular properties in that kind of in plane of that two-dimensional structure. And so material scientists and engineers, mechanical engineers, basically all the engineers working together are trying to figure out ways that you can kind of combine or you can stack this 2D graphene in a way that you can kind of take advantage of this really unique property.
Yeah.
Another big area right now is not so much in the composition area, but the processing. So a lot of you've heard of additive manufacturing or 3D printing of metals and so forth. So this is a huge area. This is going to be huge for many years.
Yep.
And the challenge there is that, for example, suppose we chose to 3D print our 17.4 pH, invented back in 1952. When you process it by additive manufacturing, you might as well consider it a brand new, unexplored, untested material. It's going to have completely different properties than what it has, what we had come to be comfortable with and understand it with. So that's going to be huge in the future. And just about every major manufacturing company, all the automotive companies, the aerospace companies, consumer product companies, they are ramping up their knowledge, their expertise in additive manufacturing. It's really going to be big, but we're many years away from, I think, having an additive manufacturing economy, but I think everybody looks at that as being.
Now, back to your materials tetrahedron, right? So
Right.
If you have processed it, the same material, quote unquote, the same material, if it's been processed differently,
Different performance. Yep. So,
okay, what is the best way to prepare to become a materials scientist and engineer while still in high school? Are there two disciplines, materials science and materials engineering, or is it materials science and engineering?
oh, great questions. Okay, so one of the reasons I ended up in material science and engineering, or as it was known when I went to school here, metallurgical engineering, is because I like chemistry. And so that's a common thread among most MSCs. Not all of us like chemistry. There are some that don't, but most of us do. So that's a distinguishing feature about MSCs. So we kind of use, I like to say, we use chemistry in a very practical and meaningful way. We use chemistry to invent new materials and to modify existing materials. We use chemistry to understand why some materials fail and so forth. So best advice, and actually Janet can add later too, because she's a material scientist. So take your chemistry. A lot of material science like physics. Okay, so there's a big branch of our discipline that's very physics oriented. So the semiconductor area, microelectronics and things like that. So Intel, for example, Intel is basically a material science company. It's all about the processing of these, silicon and these of these materials for a particular application. So those folks kind of tend to be on the physics side of things. So chemistry, physics, your sciences basically is what I'm saying.
Yep.
And then of course, math. If you know your math, you've got an edge. Okay, it'll always give you an edge if you're good at math. Again, not all of us are, but if you can kind of focus and concentrate and pay attention to your math skills, that'll give you a good edge too. That's probably true of any engineering discipline. So Janet, you're an MSc. Do you have anything to add?
Well, I didn't know that there was an undergrad degree in material science and engineering. The university I attended at the time didn't have an undergraduate degree in that area. And so and I don't think too many high school guidance counselors know about the field. And so it's a field that truly blends, it crosses all engineering fields because everything is made of something. And like Dr. Kampe was just saying, all engineering majors, it's chemistry and physics. Everybody has to take chemistry, everybody has to take physics, everybody has to take calculus. And notice I said has to take. So these were not joyous experiences for me. I had to work really hard through those classes, but then I got to the fun classes, the material science classes and things. So you don't have to love math to be an engineer. You just have to be able to do math. You don't have to love chemistry to be an engineer. You just have to be able to do it. So, and if chemistry is not your bag, material science is probably not for you. But again, you don't have to truly love chemistry to be a materials engineer. And I talked about this while we were kind of warming up. So I think personally, what I love about materials science and engineering is I can explain why we can bend a paperclip, and I can explain why we cannot bend a rock, right? So, chemistry doesn't ever actually come out and explain that part, but in materials science, we can explain it, but we have to use the D word.
Yes.
All right, let's go to our next question.
For that question, this is great. Are there two disciplines, material science and materials engineering? Actually, there could be. A lot of us view ourselves kind of more on the science side. We might be material scientists. There are chemists that consider themselves material scientists. There are some among us that kind of wear the are materials engineers with a capital E. They wear the engineer hat, so they're kind of more involved in the application side of the tetrahedron rather than kind of the early development and the description using atoms and electrons and stuff like that. But I think it's great that we have a discipline, material science and engineering, so you can kind of span that whole continuum between the chemistry, the real hardcore science, but for a purpose, for the purpose of putting it in or making something useful. Okay, so that's the engineering part.
Yeah.
So there are programs that kind of focus more on the engineering side, some that focus more on the science side. I think nowadays most programs kind of have a nice blend of both.
Mm-hmm.
And certainly Michigan Tech is like that.
All right, and this is a comment from Paul. And he says the D word can be dislocations, but it is not also true. Is it not also true that scientists or metallurgists are often known to always say, it depends, much to the frustration?
Yeah. So that's the universal answer to any question. So I could have used that to Walt Lang's question about, the effect of materials on surfaces. I should have just said it depends. but which would have been true. But I don't know. I wouldn't be able to explain much of that. So that is true. So again, that's part of the maybe the science part of things, you know. So it depends. It kind of depends on a lot of things. So it depends on the elements that you have in there, the mix of elements, something that we call the phase diagram, how it's processed, how it's made, and so forth. You know, so people say, you know, 17.4 pH strong. We can always say, well, it depends. It depends on how it was processed. It depends, you know, what property you're actually measuring, you know, these kind of things. So the D word, so that is, yeah. So maybe that's a lowercase d word, depends.
Awesome. All right, so this next question is from Roger, who I believe used to garden for Mrs. Frim in this house that I own now. He's a civil engineering alumnus from class of 68. So Roger comments, I wasn't taught about fracture mechanics as a mode of steel failure. Since it has big application to steel structures, can I assume it's taught to civil engineers now?
I don't know if that's in the civil curriculum or not.
Do we teach it to
Well, fracture mechanics would be something where, you know, the property called K1C or fracture toughness
yes.
would be in play. That would be the material property that would be useful.
And that's not in the basic intro class for most of the
I would
engineering.
guess that there are civils that go down the street to the mechanical engineering department where I know they teach fracture mechanics.
Mhm.
I'm sure there are civils that are welcome in those classrooms, obviously.
Yeah, no, very interesting. All right, so
a question about double majoring.
yeah, go ahead, take that one.
Okay, so that's a good question. If you were to get a double major in MSc in another discipline, which would be the best combo? To students often minor or double major in MSc at Michigan Tech. Answer is yes. Great question. What a dynamic combination you would have if you had MSc coupled with anything else. Okay, so mechanicals, dynamite combination. So mechanicals are great at designing. They're great at integrating different subsystems into large components and so forth. And wouldn't it be great if, you know, as a mechanical engineer, you have kind of an intimate knowledge of, you know, the materials that you're putting together. Microelectronics, dynamite, material science, and electrical engineering. Okay, so all the chips that are developed that the electrical engineers utilize in computers and so forth, you know, all of those are being developed and processed by kind of material science principles. Civil, chemical, there's terrific dynamite overlap with any discipline because just about every discipline, all disciplines, I'll just say all disciplines, you know, materials that whatever their product is, they're going to make it out of something.
Everything is made of something.
The more you know about that something, or where it came from, or what the logic was for why they use that material, the better off you'll be. What an edge.
Well, and it's there's a language. So I don't know, you know, I don't know if it's been something that you can kind of absorb by hearing these different disciplinary people talk, but each discipline has its own language. And if you can actually speak two disciplinary languages, boy, do you have a cutting edge.
And we do get, in MSc at Michigan Tech, we do get several dual majors or double majors that come through.
I know.
We offer.
I always say don't do it because I've got my thermometer is making an alarm. All right, Steve, why don't you take the next question while I go?
Is that, have you ever looked at the other half of the material connection? Okay, so so the ball construction. So that's a great question. There's probably as much folklore associated with golf balls as there are golf clubs, you know, hollow centers, liquid centers, compression, how they wind it and things like that. But personally, no, I've never gone to the golf ball. Advantage of the golf ball is you can learn more. You know, they're not as expensive. You can slice them in half and you can look inside and you can learn and so forth. But there is, as much folklore and as much probably technology associated with golf ball construction as as the clubs. So I haven't done that, but okay.
Very good. All right. So I wanted to show you what was alarming. So my indoor-outdoor temperature gauge was alarming.
Oh, so it's 6 or no?
Well, we were playing how can we make the house cooler games, and so I took the outside sensor and we were putting it in the attic. We were putting it all over the place, but somehow we set an alarm up on our indoor-outdoor temperature gauge. But anyway, sorry for that. All right, Mike asks, have you ever looked at the other half of the material connection and ball construction?
So I just answered that.
Okay. All right, what's up next then?
What made you decide to go into metallurgy? So similar experience as Janet. I didn't know anything about the field until I came to Michigan Tech. As part of the curriculum that I started in, there was a material science course, and went to that course, and wow, you know, he's talking about atoms and electrons, and this is why this metal is strong, and this is why this, you know, ceramic is brittle, and this is what ductility is from an atomic level. And again, I think I mentioned, you know, chemistry was one of my favorite subjects, and wow, here it all was. So the why factor, you know, why do things behave as they do? And so that's why. So when I was in school, there was no material science and engineering discipline at that time. So there were across the country departments of metallurgical engineering, people who, you know, dealt with metals. There were departments of ceramic engineering, not at Michigan Tech, but around the country. And then the polymer materials were kind of handled by the chemistry departments and the chemical engineering departments around the country. And sometime in the mid-90s, National Science Foundation started this initiative to try to group all these people together. They, you know, recognize that we have similar goals and objectives, and we basically think of things the same way. Kind of start with electrons, move to atoms. If you look at my screen right there, electrons, atoms, then lots of atoms make crystals, and then a lot of crystals together makes the stuff that we make. So they kind of recognized that these three separate disciplines kind of all were very similar in how they thought and so forth. And so they kind of advocated that these disciplines merge into this discipline that we now know as material science and engineering. You know, all materials are basically kind of under the umbrella of an MSc department. Some of us in the departments have expertise in different material forms. So my degree is in metallurgical engineering. So I'm still very fond of metals, but I kind of moved into, again, through my career paths, moved into composites and also ceramics. You know, I did a lot of ceramics in my career as well. Not too much polymers, only to the extent that they were present in my composites and so forth. So, again, get a long answer to a quick question. My entry into material science and engineering was through metallurgical engineering, which was one of the forerunners of MSc. It's what was available to me and what I learned about when I came to Michigan Tech.
Well, and it's one of the historical strengths of Michigan Tech, because of course we were founded in 1885 because of the need for mining engineers, and because of all the copper that was found as in its native form in the area.
Right.
And so
the original charter for Michigan Tech back in 1885 was to establish, the legislature is to establish a school to teach mining and metallurgy. Okay, so those are the words in the original legislative charter. And so originally the only degree for many years was just mining engineering, but there was a metallurgy, kind of a metallurgical department or staff that was on campus to kind of support the mining activities.
Yeah.
So it's a different kind of metallurgy than what I do. So it's kind of what we call extractive or mineral processing. So the science of pulling elements out of minerals. Kind of my area of metallurgy was what we call physical metallurgy, which is kind of physical properties associated with kind of engineered forms of the materials.
All right, so this next question is about clubs. It's from Zach. What condition do you keep your clubs to prolong their service life and mitigate corrosion? Alternately, have you ever noticed any corrosion at the boundaries of dissimilar metals or materials on your clubs?
Okay, good question. To answer it, I don't do anything other than just kind of brush the dust and the dirt off my clubs. This is kind of one of the things, leap of faith. You hope that whoever specified or made the club knows something about metallurgy to the extent that they would pick the right kind of materials that wouldn't corrode. So there's a lot of stainless steel in golf clubs. So stainless steel, as doesn't rust. Sometimes we get kind of surface rust and discoloration and so forth, but for the most part, it doesn't rust. Copper, my beryllium clubs, it's conceivable that those could undergo some kind of embrittlement, but so far so good. It's been 20 years or something. So far so good. So nothing there. So in general, we just hope that the guys who made them know what they're doing. So beware of fly-by-night golf club companies, and there are several of those. So,
I have so
so
many.
that's a quality issue. That's a quality issue, right? You pay for good quality too.
All right, so this could be from somebody Darwin.
Yeah, Darwin.
Darwin, BSME 1979. So you may know Steve in person. Can you briefly discuss the current state of damage tolerance on aerospace composites? And he speaks about significant work having been done in the 1990s on composites.
Yeah. So 1990s, there was a lot of activity in the aerospace industry, sponsored by Department of Defense, for a variety of real high performance systems, that they needed, high stiffness, low densities, low weight, and so forth. Unfortunately, that combination, as Darwin has correctly pointed out, there's some real severe issues with what we call damage tolerance. So they would tend to fail by fracture. So instead of just bending out of shape, which is a good clue that you've exceeded the design stress of your material, instead of just bending out of shape, which allows you to land the airplane and look at what the problem is, they would tend to just break, which is a catastrophic form of failure. And so that's obviously, so there's a lot of effort put into kind of understanding failure by fracture if you're going to use these advanced materials. So I don't know a lot of details about what they did. Some of the strategies that I was aware of, they were looking at ways to make, there's some kind of tricks that you can do to design with thin sections. So thinner materials kind of non-intuitively can actually be tougher than thick sections of materials. And so if you, if you created designs with kind of series of thin sections, that could be helpful. There's an effort, big effort for a long time to make ceramic composite turbine blades. Wow. What were they thinking? But there is some good science, there's some good engineering that basically
except when bird strike happens, right?
Right. This is another thing. So bird strikes, that's a big test. So there are bird ingestion tests into jet.
I know. they do thaw them first before they fire them.
Because that's harder. I mean, I think it's a more severe test if the bird is thawed, I think.
I bet.
I don't know. That was and still is an active area of research in aerospace materials, because again, the trend in aerospace materials, make it stronger, lighter, stiffer. None of those things are good for damage tolerance or toughness. They're all great for strength, but damage tolerance, the ability to kind of withstand abuse, withstand, someone beating on with a hammer, that is the challenge. And that's what really limits kind of our use of these materials. I tell my students, ceramics are wonderful materials. They have huge, really high strengths. But the fact is they're not very tough. Okay, so it's too bad, because you could really tap into those high strengths of ceramics. You'd have something really special. You'd have a corrosion resistant, high strength, pretty, good looking material, because they come in these really neat colors and
Yeah.
textures and so forth. So, but they're just not taught.
I was going to say, I always thank the audience who is still with us. So we still have 45 people with us, and it's already 7:12, and I hadn't thanked you yet. So thank everyone. We still have 6 open questions, and we're going to kind of finish our way through them. But just thanks again for joining us. I've had so much fun hanging out with you guys and talking about material science. All right, the next question's from John. What are some examples of the Michigan Tech Materials Science Research Project's area of focus, quote unquote, unsolved problems? So answer that one first. There's a second part.
Okay, so some of the activities that the faculty here in the department are working on, doing some great work. Eric Herbert's working on lithium-ion batteries. John, you actually sent us an email today about some work on battery technology out of Berkeley. And so Eric has been working on exactly that problem, or the problem that what you sent us is seeking to solve, and that's the presence of dendrites. Again, that's a kind of a type of crystal and form that forms within the material, and how that can cause the battery to fail and overheat and so forth. So Eric Herbert and Steve Hackney are doing some great work there. Joshua Pierce in the department, photovoltaics, okay, so solar energy, sustainability. Joshua works on a lot of technologies that try to seek or that try to solve big problems in the world, okay? Problems that underserved rural populations have. So energy, manufacturing. He also, oddly, you might think it's odd at first that someone who works in photovoltaics might also work in 3D printing, but he works in 3D printing because that's a means that underserved areas of the world can manufacture things. So there's that. We have several faculty who work in what we call functional materials. So a good example of a common functional material is a piezoelectric. So you've probably seen little kids' tennis shoes. They're walking down the street, and as they walk, a little light flashes.
Mm-hmm.
Piezoelectric. So the way that works is, as that material experiences stress or a load, so when they walk on it, it generates electricity. So that's called a piezoelectric. That's called a functional material. There's also materials that do the same thing. You generate stress and it'll magnetize it. You magnetize it, it will create a current. You create a current, create a stress, all these different kinds of interrelated functionalities. So these are called smart materials. So you put in one kind of stimulus and it does something else, or some kind of, it seems like it should be unrelated, but they're actually related at the microscopic and electronic and atomic level. So we're doing that. Paul Sanders in our department, material design, kind of new compositions, new strategies for designing materials on the computer, works very closely with the automotive industry, works with the casting industry as a way, again, the process and the structure kind of link to performance.
Right. So John, you've asked the department chair about all the research. And
yes.
I'm going to cut you off there, Steve.
Okay.
And I would like to make a plug though. So all of the chairs are always looking for great senior projects. So if your company or has an idea for a senior project, send Kampe an email, or the chair of the department that it might best fit into. And Steve's email is just Kampe, Kampe, @mtu.edu. Thanks for your question, John. So Larry gives an answer to the perimeter weighting. And I'll just read it. Perimeter weighting brings a more consistent hit because more of the weight of the club is focused at the site of the impact with the ball. Less movement of the club further away from the ball. P.S. If my name looks familiar, yes, I am that guy who was in DHH.
Right.
So Larry. We're both undergrads. All right.
Larry,
hi, Larry.
Darwin Moon is part of this webinar as well. And I think I mentioned your name to Darwin as someone that was on campus recently, and a name that I, for some reason, I'm thinking you two knew each other, but I might be all wet, but I don't know. So.
All right, and if Roger Smith is still listening, I hope you are. The chair of the department says, yes, fracture mechanics and the mode of steel failure is still taught. We have an undergrad materials class that introduces the concepts, and we have 2 steel design courses undergraduate students can take before they graduate. So thank
Okay,
you.
good.
More.
Yeah. So
Good to know.
sorry for not knowing that, Audra.
Yeah, no, interesting. So this next question is from Smruti. Hi, Dr. Kemp. Most of my friends transitioned from EE to M&M time to time in their career. I was wondering how closely these 2 fields interrelate. Is it possible to get a dual major in EE and MSE?
Yes, of course. So like I said, we have several dual degrees students in MSE here. And again, you know, MSE plus any of the disciplines, it's really dynamite. I mean, I think it's great. It's a huge, you know, it's a huge feather in your cap if you could become an engineer. You know, the other engineers, the non-MSE mechanicals, electrical, civil, they make products, you know, they make, microelectronics, and they build cars and stuff like that. But kind of before that, they're picking out the materials that they're going to use to be successful. And wouldn't it be great if you can wear both hats as you kind of work on those products on the performance side of the tetrahedron?
Very good. All right, and so this next question is from one of our favorite alumni who was mentioned earlier. Has anyone introduced CFC club heads yet? The shafts have been in use for many years. Tungsten and/or carbide inserts were proposed for Big Bertha supersized CFC driver heads in 1990. And it goes,
right. Yeah.
And then he asks, weren't you a student under Dale Stein? And I think the answer was yes. He had been a principal in the development and intro of Auger surface spectroscopy equipment while a professor at University of Minnesota prior to joining Michigan Tech in the 70s. So Dale Stein was our former president.
He was president when I was an undergrad, and he actually did come into the classroom and teach some lectures to the undergrads while I was a student here. And
yeah, no.
Dale was internationally renowned when he came to Michigan Tech in the early 70s, I think, or maybe the 60s or something. He came as faculty member, became chair of MS, or the metallurgy department, became provost, and then eventually became president after Ray Smith. So, yeah. And he's a good golfer. He's a scratch golfer. So he's responsible for what we call the new clubhouse up there.
All right. So John asks, is there a branch of material science engineering that focuses on materials recycling? And
that is yes. We all do.
Related questions, yeah.
Yep, we all kind of think about and worry about recycling. So has a lot of impact on kind of a lot of metrics that we use to design materials. Obviously, if you recycle, you know, it reduces your embodied energy, or the amount of energy that you have to take to build a new material or a new component. We try to select materials that are recyclable for that reason. Mm-hmm. So we tend to be pretty forward thinking, I think, in terms of sustainability of the planet. And I think we recognize that we're in a position to actually do something about it and to make decisions that will be helpful in the future for these kind of things.
Well, and there is a focus at Michigan Tech for sustainability. So we have, and I'm not the right person to pull up those facts. Do we have a minor, is it right, in sustainability?
We probably do. We have the Sustainability Institute. It's an interdisciplinary institute that Dave Shiner runs. Yep. So a lot of our students there. So is there a focus at Michigan Tech for teaching how to design materials that may be reused multiple times? I would say that's a routine component of our material design, our material selection and design course.
Yep. We have a faculty member in chemical engineering who actually is focusing specifically on that, and I'm not going to be able to pull his name up.
Lee Pan.
That's it. Thank you. Lee Pan is doing research specifically on that area.
Yep. So we work with Lee Pan on kind of helping him identify, you know, what would be helpful if he could pull out of the recycling stream and these kind of things.
Very good.
And Lee Pan is actually, yeah, so he's the one doing reusing lithium ion or recycling lithium ion. So.
All right, and And we are close to the end. I think we have one or two questions left. So one question asks this: for sustainability and the future health of our planet, what is the most important area of materials engineering that needs to advance to make a difference?
That's a huge question. Obviously, the first thing that comes to my mind is photovoltaics, so solar energy. The photovoltaic is a unique material, converts sunlight to electricity, and it's far from optimum. It's far from being perfected. And certainly, if you think about the kind of impact that could have on our planet, to basically reduce or eliminate the dependency on hydrocarbon fuels, huge. And then sun is available everywhere, maybe less so in the Keweenaw than other places of the world, but there's still lots of it. And so I think that's a big one. And I think, lightweighting, fuel consumption, reducing fuel consumption, things like this are all huge opportunities that are here for engineers to take advantage of and make work.
Well, so we are wrapping it up at 7:22, just in time for Jeopardy, if that's something that you do. And we still have 39 total participants. We had 29 questions answered. Thank you so much for your curiosity. This has been a really exciting topic for me. And so Steve Kampe, Dr. Kampe, thank you so much for your time this evening and for teaching us so much.
Okay, thank you. And feel free to email me if you have any inside information on golf clubs or other items that, interesting materials, curious materials of construction and so forth.
Or if you just want to check in as an alumnus and say, or future student. Remember, one of the things, I guess, I don't know if this is remember, but one of the things we've been teaching in the Tips and Tricks Tuesday night series is that your chair is actually an important person to you as a student. So the chair, actually their role is to supervise the faculty and staff in your department, and your degree program resides in your department. So if your major is material science and engineering, Dr. Kampe is your future chair or current chair. So thanks again, Steve.
Sure, I enjoyed it.
Good night, everyone. See you next week.